Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Dokwa Jr., your math tutor and an instructor of mathematics at the University of Liberia. In my today's lesson, I will be continuing on methods of differentiation, and we will be doing the proof of the quotient rule. So in previous lessons, we started with the first principle of derivatives, how to find the derivative of a function using the first principles. So since we know the definition of the first principle of derivative, we're going to use that definition to show that if f of x is equals to small f of x divided by small g of x, f prime of x is equals to g of x times f prime of x minus f of x times g prime of x, or divided by g of x or square. So this is what we're going to prove. We want to prove that this is actually equals to this, right? The derivative of this f function is equals to this. So we know that the first principle of derivative, the definition of the first principle of derivative, that is definition of first principle of derivative is, now we have f prime of x is equals to the limit of f of x plus h minus f of x divided by h as h approaches 0. Now, this is one thing that we also need to note. This definition can take on any function. For instance, we will also say g of x, g prime of x. So the only thing we're going to change here would just be this capital F to g of x plus h minus g of x all over h as h approaching 0. We will also say, let's change this capital F of x to small f of x. So this definition can take on any other function, right? We could even say p of x, we could say q of x, we could say h of x, arrow of x, or whatever the case might be, right? So now we want to use this first principle of derivative. Normally we call it the limiting process. So we're going to use this first principle of derivative to prove that the derivative of this particular function is equals to this function. So now let's start. So the first thing we need to identify here is our f of x. We know that our f of x is equals to f of x divided by g of x. We know that, right? So we're going to replace this capital F of x with this function. The next thing we need to identify is what is our f of x plus h. So now f of x plus h, it tells us that wheresoever we see this x, we must replace it with x plus h within this particular function. So we rewrite this function f of x divided by g of x. So wheresoever we see this x, it must be replaced with x plus h. So we put x plus h, we put x plus h. So this is now our f of x plus h, and this is now our f of x. So we've gotten the two functions. We can now replace them within this limiting process. So we say capital F prime of x is equal to the limit of, now capital F of x plus h is what we have up there, which is small f of x plus h divided by g of x plus h minus f of x divided g of x, all divided by h as h gets closer and closer to 0, or we say as h is approaching 0. So we simplify. This is a complex fraction. So we simplify. So we have f prime of x is equal to the limit. So we take the numerator. We find the LCD for this and this, which will just be g of x, this times this, right? And g of x plus h. So whatever you put first, it doesn't matter. Now, so g of x plus h goes into this denominator. G of x plus h will cancel g of x plus h. You'll be left with g of x. So it's g of x times the numerator. So we say g of x times f of x plus h minus g of x goes in this denominator, which is our LCD now. G of x will cancel g of x. We will be left with g of x plus h. So it's g of x plus h times this f of x. G of x plus h. Now, there's a complex fraction. We have this divided by, so it's like divide h, right? So what can we do? If we change this sign to multiplication, we can reciprocate this h over 1, and it will be 1 over h. If we multiply this h by this expression, we will just have h times g of x times g of x plus h, right? So this 1 over h will not be there, as h is approaching 0. Now, we continue. We say f prime of x is equals. Now, what we can do here is we can factor out this. So we factor out that expression. We're going to get g of x times f of x plus h minus f of x g of x plus h. So okay, let's factor it first. So if we factor out this expression, we're going to get 1 all over g of x times g of x plus h times then this entire numerator divided by this h. So we have h, then g of x, f of x plus h minus f of x, g of x plus h. Now, we know that if this limit exists, if this limit does exist, that is, if the denominator is not 0. So if this limit does exist, it means we can take the limit of this first factor, this or factor, and we can also take the limit of this second factor. So thus we can say, I'm going to just g of x plus h times, so we can take the limit of the second factor, the limit of g of x plus h times f of x plus h minus f of x times g of x plus h divided by h as h approaches 0. So we took the limit of the first factor and we took the limit of the second factor. So here we can apply the limit. So let's move upward. So if we apply the limit here, that is, wheresoever we see h, we should replace it with 0, since h is approaching 0. So we have f prime of x is equals, so when you are applying the limit now, you no longer write this limit. So we have 1 all over g of x times g of x plus 0 times the limit of g of x f of x plus h minus f of x times g of x plus h divided by h, as h is approaching 0. Now, so in this first case, so in this first area, we have f prime of x is just equal 1 all over. Now, if this is 0, it means you will just have g of x times g of x. So this will give us g of x all square. Now, what's the next one? This is the next area now. What we want to do here, we want to apply some tricks such that we can arrive at this definition. So we can apply some tricks. So we say g of x times f of x plus h minus f of x times g of x plus h. Now, what we can do is that we can add f of x, g of x, and we subtract f of x and g of x. It's just the same thing, because this minus this, it goes out, right? Now, why did we choose to add f of x times g of x and f of x times g of x? Why did we choose to add and subtract this particular expression? The reason is because here we have f of x plus h, and here we have g of x plus h. So if this is f of x plus h, what I need to be attached to this f of x plus h to give me this particular definition is some f of x. So I need to have some f of x attached to this f of x plus h. For this g of x plus h, I need to have some g of x so that I can arrive at this definition. Because this is equal to f is equal to g prime of x, and this is equal to f prime of x. So let's assume that this was small f, and this was also small f. Now, so that was the reason why I added f of x plus g of f of x times g of x, and then I subtracted the same expression divided by h as h approaches 0. So I have f prime of x is equals to 1 all over g of x all square. And what do? I group them. But mind you, because there is a negative sign between this function and this function, I must group them in a way that I will have this negative sign. So I group the first. I cannot group the first term and this term. I cannot, because this is positive and this is also positive. So I group the first and the last term. So you see, g of x is in this expression. G of x is in this expression. So if I factor out g of x, I will be left with f of x plus h minus f of x plus h minus f of x. So I have the limit g of x times f of x plus h minus f of x g of x divided by this h. We know that this h can be distributed as h approaches 0. So there's the first one. The next is I have this and this as well, right? These two. But if I factor out this negative, it means this first expression will be positive and the next one will be negative. Why am I factoring out negative? It's because the negative is attached to the g of x. It's not attached to the g of x plus h. It's attached to the g of x. So I factor it out. So I also take the limit of this second function. So I have f of x, g of x plus h minus, because this will be positive now and this will be negative, f of x and g of x divided by h as h is approaching 0. Great. So we factor out. So we now have f prime of x 1 all over g of x all square equals, times now. So if I factor out this g of x, because g of x is common to the two expressions, if I factor out g of x, I will have the limit of f of x plus h minus f of x divided by h as h approaches 0. So I can clearly see that this expression right here is just equals, this expression is just equals to f prime of x. And then on the other hand, minus, if I factor out f of x, I will have the limit of g of x plus h minus g of x divided by h as h approaches 0. So again, what am I going to see on this side? I'm going to have g prime of x. So therefore, I will have f prime of x to be 1 all over g of x all square times, the first one is g of x, and then this is f prime of x, minus this is f of x, and then this is g prime of x. So this is 1. So if I just interchange them, I can further simplify this expression as g of x f prime of x minus f of x g prime of x, all divided by g of x raised to the second power. So this is the proof. So what is this trying to tell us? This is simply telling us that whenever we have a function capital F of x, and then you have a numerator which is a polynomial function or whatever function it could be, just any function, but you have a numerator and a denominator in a quotient form, right? What you're going to do is that you are going to take the denominator and square it. So whatever expression that is right here, you just square it. And then for the numerator expressions now, you're going to take this g of x and rewrite it. So we see that g of x has no derivative notation, no prime attached to it. So we're just going to rewrite this denominator, and then we multiply it by the derivative of f of x. So it means we're going to find the derivative of f of x minus, what next again? We rewrite the numerator because we have initially differentiated f of x. So we just rewrite f of x, and we now differentiate the denominator. So to just show you something very simple, if we have f of x, assuming we have f of x is equals to x plus 1 all over x plus 2, for example. So in this expression, our f of x is equals to x plus 1. So let's say this is s squared plus 1. So this is s squared plus 1. And then our g of x is equals to x plus 2. So the rule says to find the derivative, which is f prime of x, we take this denominator, x plus 2, we square it. It can be whatever expression in the denominator, just square it. Then we move up. In the numerator, this denominator, we hold it first. So we always start with the denominator. So we rewrite the denominator, x plus 2. And then we differentiate the numerator, x squared plus 1. So from our previous lessons, we know that the derivative of x squared, it means we should bring this 2 down, which is 2. And we subtract 1 from this. So it will be x now raised to the first power. Right? So this gives us 2x. And then the derivative of a constant, derivative of any number is just equals to 0. So whatever number it is equal to 0. Why is it equal to 0? Because if you have 1, it means there is an invisible x raised to the power 0. 0 times 1 is 0. So you don't even need a continuum because that entire expression will be 0. So we've differentiated the numerator. Then the rule said we should attach a minus sign, and we rewrite f of x, which is the numerator now, x squared plus 1. Please make sure that always put it in parentheses so that you don't get yourself confused or you don't mess up the sign. And then you differentiate the denominator. So the derivative of just x, because x raised to the first power, if we bring this 1 down, it gives you 1. X, you subtract 1 from the power according to the rules of derivative, it gives you 0. Any expression raised to the power 0 is just equals to 1. So there is just 1 times 1, 1. So the derivative of x raised to the first power is just equals to 1. And the derivative of 2 is 0. So this is how we apply the quotient rule. This is exactly how we apply the quotient rule. Then we simplify. So we have f prime of x. So what do we have? 2x times x is 2x squared, and 2x times 2 is 4x, minus x squared times 1, we have minus x squared, and then minus 1, divided by x plus 2 all squared. So what would this give us? 2x squared minus x squared is just x squared, and then we have plus 4x, and then minus 1, divided by x plus 2 raised to the second power. So this is actually our answer. So this is how we actually solve problems involving the quotient rule. So in next videos, we're going to solve numerous of other problems involving the quotient rule. Also, in some books, you will experience that the notation for f of x and g of x is being replaced. In some books, you will see f of x is equal, or they use y. In some books, you will see y equals to u over v, or some will say v over u. So this u is representing the numerator, and this v is representing the denominator. So to rewrite in this form, we square our v squared. The rule said we should hold v in the numerator and differentiate u. So we have times u squared, minus we hold u, and then we differentiate v. We get v prime. So just make sure in the numerator that both u and v is differentiated. But always start with v so that you don't get the sign mixed up. Okay, now what if we want to use the method of differentiation? That is, we want to use the okay, so in next video we're going to talk more about that, right? So we're going to talk more about that. So this is how we deal with the quotient rule, and follow us in our next section where we're going to solve a lot of other problems, some challenging problems on how we can find the derivative of a function using the quotient rule. So thanks also much for watching. See you in our next video. Thank you.